Good morning. Once again, it's the physics video lecture. Physics 105A video lecture 16. I'm going to start by just repeating a calculation we did the other day, and then we'll move on. But we're on this topic of damped oscillations for a little while. So let's go ahead and start with the differential equation. And we are looking at, well, I'll even put Newton's law here. On the right side we have So if we start with Newton's law, we recognize mass times acceleration. There's the linear Hooke's law type of force. And then we have a friction force that opposes the velocity, that's your minus sign, and it's proportional to the velocity. So there's a constant there. But we then introduced some other constants in order to bring us to this form. Two derivatives, 2 gamma, the first derivative, plus omega naught squared, the 0th derivative equals 0. So there's our linear differential equation. It's second order. It has constant coefficients. And the general solution is an exponential. And I'm just going to set up the exponential a little different this time, but we're going to do the same calculation before. That'll give you confidence in this. So general solution is going to be complex. So we'll use the letter Z. It's going to be a complex constant, e to the lambda t. Okay, last time I did e to the I omega t. We're going to see we get the same answer out. This is a complex lambda. And again, we go into this differential equation, A star, take 2 derivatives plus 2 gamma times 1 derivative plus omega naught squared times the function itself. And that gives us the 2 derivatives. So good. Leads to or gives lambda squared a e to the lambda t plus 2 gamma, and then the first derivative brings a lambda down, a e to the lambda t plus omega naught squared times a e to the lambda t equals 0. So clearly, again, we just factor out this polynomial, lambda squared plus 2 gamma lambda plus omega naught squared equals 0. Right now we're not seeing any imaginary parts, but we're confident, especially we will be after we do this, that this is the general solution. So once again, 2 derivatives with respect to time brings lambda down twice, and then plus 2 gamma, 1 derivative brings lambda down, and then no derivatives. And we factored off the a e to the lambda t. So now let's go ahead and solve using the quadratic formula. 1/2 b squared. This time b squared is just 4. No, not b squared, negative b. Sorry about that. So minus 2 gamma. So negative b plus minus the square. We all know our. So negative 2 gamma plus minus the square root of 4 gamma squared minus 4 omega naught squared. And we're just going to look at the underdamped case this time. So what do we have? Lambda equals negative gamma plus minus. And remember, the underdamped case is if omega naught squared is greater than gamma squared. So this is a negative number, underdamped gamma squared less than omega naught squared. Okay. So what we can do is we can reverse the signs. We've got a -1 then, we pull it out as an I. So we have plus minus I root omega naught squared minus gamma squared. And then we go back into our general solution here. I'm going to skip a step. We're going to go back into the general solution and take the real part. But let's go ahead and not skip a step. So let's see what we have here. We have z equals a e to the lambda times t. So we have e to the minus gamma t times e to the plus or minus I root omega naught squared minus gamma squared. Haven't skipped any step. And when we take the real part, it's not going to matter what's the plus or minus here, because both times it'll be the cosine, because the cosine is a symmetric function. So finally, real part, so x of t equals the real part of z here. And I'm going to do that same trick I did where I have a equals magnitude of a e to the I alpha, which is something we can do for any complex number. And so I'm going to have an e to the I alpha multiplied in there as well. Forget the t right here, t. And the e to the I alpha will not be multiplied by t, so we end up with magnitude of a e to the minus gamma t cosine root omega naught squared minus gamma squared plus alpha. So there you have it. Again, these are our damped oscillations, and we see that this is an oscillatory term clearly, and this e to the minus gamma t, there's the damping, exponential damping of our solution. So we had seen that as well. I'll just graph it one more time. Okay, and the phase could be anything, but we'll let the phase be 0. We have within this exponential envelope these oscillations here. There you go, damped oscillations. Now I want to go a step further and show that the general solution of this form actually even holds true for matrix differential equations. And that'll give us a good chance to do a little bit of matrix multiplication, matrix times vector, that kind of thing. So let's see. Actually, before I do that, before we talk about matrices or anything else, let's quickly talk about the energy of the damped oscillator. Clearly, the energy is decreasing because the amplitude's decreasing, and if you wait long enough, the thing comes to a stop. Well, e to the minus gamma t gets very small. In reality, it'll come to a stop, and the energy's gone. Okay. And what happened to the energy? Well, it probably got chewed up in the friction there. Okay. So let's talk a bit about the energy. Remember, we had the energy of the harmonic oscillator, which was constant. So I'm going to, actually I'm going to leave the equation of motion up there because we're going to use it. So I'll erase this and talk about the energy of damped oscillations. equals 1/2 m x dot squared plus 1/2 k x squared, right? Kinetic plus potential energy of the damped oscillator. Well, the energy is clearly decreasing, but if you want to, do we have the solution up here? Will I erase the solution? Well, we're going to have to rewrite the solution here. So we have x of t equals a cos root omega naught, well, actually minus e to the minus t, let's put that back up there, e to the minus gamma t cos root omega naught squared minus gamma squared t plus alpha. Good, we want the energy of this thing, and I don't have to write the absolute value signs. This is a real constant right now. So we want the energy of this thing, and it's no longer going to be constant. If we take these derivatives, the expression is going to get a little bit messy, right? We have a product rule here. So I'll just take the first derivative. So our x dot is equal to minus gamma a e to the minus gamma t cosine of the argument. So then we have to have product rules plus a e to the minus gamma t. Then when we take the derivative of the cosine, I guess we get another minus sign out. And the inner derivative I'll put here, root omega naught squared minus gamma squared, and then we'll have the sign of root omega naught squared minus gamma squared t plus alpha. So there is our velocity. Now whoever wants to square this thing and plug it all in can. Of course, in the limit as gamma goes to 0, we will end up with a constant energy. But the point is, if we were to square this thing, plug it in here, get the original x, square it, we're going to get something complicated. But what I will do is start squaring it, because what we can easily do is just deal with this here first. So energy is going to be this 1/2 mx dot squared, 1/2 kx squared. It's always going to have 1/2 that we're going to multiply it by, and then a squared e to the minus 2 gamma t. So we definitely have 1/2 a squared e to the minus 2 gamma t times a bunch of oscillating stuff, okay? So this proportionality is good. As it gets complicated stuff, okay? It's, of course, again, in the limit as gamma goes to 0, the whole thing just turns into 1/2 a squared k squared, ka squared. So I'll even put this as a note. When gamma goes to 0, E of course turns into 1/2 k a squared, as it was before, okay? 1/2 k a squared. What we want to do now is get a handle on this thing. What's going on? So now we have an envelope for the energy. I'll graph it right here. Okay. So the energy in this system is always positive. There's T. There's 1/2 a squared. But I'll just write E sub 0. So this is energy. Now since it has this exponential envelope, we can draw that. And something's going to be going on in between there. And depending upon the magnitude of gamma, it decays more or less fast. I should give it a little more form here. Okay. You get the idea. So what's the nature of what's going on here without multiplying this all out? By the way, if you're interested, go ahead and multiply it all out and admire it. Okay. What we're going to do is a shortcut, because we definitely see what's happening. It's decaying. We're going to do a shortcut by looking at the derivative of the energy and reusing this differential equation here. Okay, so this is an interesting trick. Go ahead and, because I want to use that equation there, so I'll go ahead and leave it out for us to look at. So what are we doing here? To understand E of t, take the derivative. Take the derivative. So what is dE dt? That's the time derivative of the energy. Is it still written of it? The time derivative of this, okay? Of that energy up there. So of 1/2 m x dot squared plus 1/2 kx. So here we go. How can that help us? 1/2 mx dot squared, so the 2's cancel, so we end up with 2 over 2. Well, I don't even have to write that. They cancel. We end up with mx dot x second derivative, okay? Chain rule. And here the 2 oh, that was an x squared. Here the 2 cancels as well, so we end up with plus kx. And since we're doing the chain rule here as well, 2x x dot. Okay. So that is, we can factor out an x dot, and we have mx double dot plus kx. Okay, so far so good. I've just taken the time derivative, it's the chain rule. But now this next step is great. We've got the x dot out here, and then the mx double dot plus kx, if we look at this original equation, which is what we're working with, bring the kx to the other side, that's mx double dot plus kx equals minus bx dot. Okay. So this is x dot times minus bx dot. And we have a great result. Maybe I'll write it in red. Okay, so what do we have here? We have dE dt, change of the energy with respect to time, is equal to minus b. And remember, b and gamma are related, of course, but that's the friction coefficient, minus b x dot squared. So the rate of change of energy is proportional to the velocity squared. The minus sign tells us, sure enough, it's always decreasing, but we have a little more. Let me continue right here. I'll continue right underneath here, so free up a little space. Yeah, where does the velocity vanish? Okay. dE dt, it's not constantly decaying, because the velocity vanishes at the turning points. Okay. what we're going to get now, I'm going to redraw this E of t, and I'll even put the envelope in like this. That's our exponential decay. So we're getting a step-like, because the derivative of this function vanishes means it'll have horizontal steps. Okay. And the horizontal steps are when, somewhat horizontal, are when that velocity vanishes there. Okay. So this is a really important lesson. Okay, let's put this thing in a box just because we can. So this is an important lesson because it is possible, and it's often possible, to learn about the solution of a differential equation, to learn about its behavior without actually solving the differential equation. What we did is we plugged the differential equation itself back in and obtained this information. So that's an important lesson. It's hard to solve differential equations, so we analyze them as best we can, and this was just a really great example of that. So put in a few words about what I just said here. I don't have on the board anymore, but of course you have it in your notes. I don't have the x dot. You could actually study that thing a bit and figure out where does x dot actually vanish. In fact, let's do that as a homework since we already have half of it there. Homework. From x of, okay, calculate, and I just did it, it's in your notes already, make sure we did it right. Calculate x dot for the damped oscillator. Okay, so you already have that. And then you want to find out, where does x dot vanish? Where does x dot is equal to zero, because it's a periodic occurrence, right? How that vanishes there, that give you that little step. So basically, you're just setting it up and expressing it in a form so you see where x dot vanishes. Okay, it's no big deal. This is something to look at. Okay, let's consult the clock. Yeah. So once we have this, right, and again, the envelope here is going as e to the minus 2 gamma t, and then we've got the structure inside. Proportional to that. Okay, so we're going to revisit this type of differential equation. In fact, we're going to revisit this equation, and by putting it in a matrix form. So our next topic is, again, differential equations, linear differential equations with constant coefficients. Constant coefficients, of which this is a great example. But what does that have to do with the matrix? Well, we can express this in matrix form. So begin, we'll just rewrite this one down, but begin with 2 gamma x dot plus omega naught squared x equals 0. And I had this one up here as well, so you you guys want to remember, omega naught squared is k over m. 2 gamma is b divided by m. That's implicitly right there. So we're going to begin with this and then define, let x1 be equal to x and x2 be equal to x1 dot, which is just x dot. Okay. So x1 is this original x and x2 is its first derivative. Then we can express this differential equation in a matrix form. And this is going to go, well, I'll send this up. Okay. So we want to express this setup up there as a matrix equation. I could assign this as well. Let's see. Rest as, I'm just going to call it a matrix diff EQ by doing the following. D over dt times this vector is equal to a square 2 by 2 matrix times the vector. What do we have there? In fact, the time derivative of x1 is equal to x2. Okay? Time derivative of x1 is equal to x2, and you know we're doing a row times column here, so this is apparently 0, 1. First row is just 0, 1. Time derivative of x1 is equal to x2. I'll write this out in a moment just to make sure we all see what's going on here. What about the time derivative of x2? The time derivative of x2, in fact, let's go ahead and rewrite this differential equation. We have, star can be written, x2 time derivative is equal to minus omega naught squared x1, okay, minus 2 gamma x2. That is this differential equation. So x2 dot, that's x double dot. And I bring these over to the other side, minus 2 gamma x2 dot minus omega naught squared x1. So we have that. And then how do we arrange that in this line here? It's going to be row times column, so it would be minus omega naught squared, the bottom left, and minus 2 gamma. So there's a differential equation with constant coefficients. Minus omega naught squared x1, minus 2 gamma x2. Okay. So far so good. Put a red box around that. Matrix times vector. Or we can just write this in the following form. D vector x dt is equal to the matrix A times the vector x. Okay, so that would be the complex form, not the complex, the complicated. Actually, this is the complicated form. This would be the simple form of that differential equation. And A is a matrix. In fact, it's an n by n matrix in the general case, and then x equals the vector x1 all the way down to xn in the general case. So we have a two-dimensional case, but there could be an n-dimensional case. And then we could have, for example, reduced, it could just stand on its own, or we could have reduced a higher order differential equation. Say instead of 2 derivatives, we have 3, 4, 5 derivatives. Okay? We could have reduced it in the same way. So this is the nice compact form. That's what I wanted to say, compact, not just a simple compact form. And the interesting thing is the general solution of this is a vector times e to the lambda t. So the general solution of this equation is, before I say the general solution, let me just say the solution, and then the general solution can be a linear combination. So the solution is x of t is equal to a vector I'm going to call lowercase a e to the lambda t. And this e to the lambda t is just the one we've been using. Exponential function with, t is of course scalar, lambda can be complex. So let's tackle this. Yeah, I can erase. I'll leave that left side up here. Okay, so we're continuing with this right here. So we've got the left side and the right side. So the left side, we have dx dt is equal to a, which is a vector, and we'll just differentiate lambda e to the lambda t. Okay. The right hand so is the left side of star, or equation up there. A times x is equal to a e to, is equal to the matrix A times the vector A e to the lambda t. Okay. Matrix times vector. Now, since this is a scalar, we can pull it out. So if these two sides really equal, then if they're equal, we should be able to say if they're equal here, I'm going to put it this way. If they're equal, of course, we can cancel the e to the lambda t from both sides. It's non-zero, and it's common factors. So they're equal when a times a is equal to lambda times a. Okay. Lambda is a complex number, a is a vector, and this is the definition, this is the defining equation for an eigenvector. Solution is, so here we go. Let's go ahead and just write that down. That is A is an eigenvector of the matrix A with the eigenvalue lambda. Okay, so you have to, eigenvector, eigenvalue. You have to remember that part of linear algebra. It's staring us right in the face. And the proof of this is going to be, what we're going to do to wrap this up is just calculate the eigenvalues of this matrix. Okay. think about doing the eigenvectors later, but let's just calculate the eigenvalues. I can erase this right here. So, example, eigenvalues of that thing up there, okay, eigenvalues of that, what do? We have, we set the determinant of A minus lambda times the unit matrix equal to 0. That's how we find the eigenvalues. So we could say, or determinant of minus lambda 1 minus omega naught squared minus 2 gamma minus lambda. That's in the corner there. Okay. So those are the 4 equals 0. And we can multiply that out to see how much time there is. Maybe you guys should do that. We can do this. Okay. So what do we have? We have minus lambda times minus lambda, so we have lambda squared. We have plus 2 gamma lambda, minus that minus, plus 2 gamma lambda, and then minus negative omega naught squared plus omega naught squared is equal to 0. Okay, well, we've been there before. That's what we just worked with a little while ago. So that's the proof. Now you would also have to find the eigenvectors if you wanted to actually construct the full solution. But since we already know it's e to this lambda t, we've already found the basic solution already. Okay? If we take the lambda from here, bring it up into here, okay, and we have that behavior of the oscillator, of the damped oscillation. The full solution, I should say something about the full solution to wrap this all up. Okay, so that was clearly a nice proof of concept right there. So the general solution, if you wanted to construct it this way, and we really don't, I've got this here. I'll go ahead and erase this now. So there's more than one lambda here, right? We know that here we have lambda plus and lambda minus, right? When we solve that quadratic equation. Here we have 2. Generally, we would have n of those lambdas for the n-dimensional case. So now I can say something about the general solution. General solution is a linear combination and let's see, we would say x of t, remember this is that vector, that's going to be a sum over all of the a sub I, actually it's going to be a linear combination, so I'm just summing, in this case, 2 vectors, in the general case, n of them. We would have I need some constants here, alpha sub I, a sub I, e to the lambda sub I t, okay, and then this alpha would be just coefficient, just some constants. These, of course, are the eigenvectors that we're would be n of them in general, 2 of them in our case, and these are the eigenvalues. Okay, so that's pretty great. That's pretty great. Yeah, make sure you recognize what we just did here. We found both, we know this thing, so we have both eigenvalues. We could have a sum of alpha sub 1, a sub 1, e to the lambda plus, right? And then another eigenvector, e to the lambda minus. For us, there's no point in pursuing that anymore because we already have the solution, but it puts it into context. And definitely, you want to know that this differential equation, first order, but vector, has as its solution, the eigenvector times e to the lambda t. So yeah, the exponential function really has to be the complex exponential function to be the full value. Okay, once more I consult the clock. I think this is a good place to stop. Okay, good. See you guys next time.